It's now time for us to do some practice using the shell method. Since we're in our application phase right now, we should really be focusing mostly on learning to set up our problems. Setting things up is very important. We can't get the right answer, no matter how good we are at integration, if we're doing the wrong integral. So make sure you can set things up. Now, of course, the way you do that is practice. The more practice you do, the better you get at making sure your setup is correct. And so do as much as you can. And if you're following along with this video, make frequent use of the pause button. And pause, try to get things set up, unpause, and let's compare and see how we did. And, well, over time, I think we'll start to agree more and more. A good sign, a good sign. All right, well, let's begin. So our first problem, using both methods of determining volume of revolution, so namely the washer method and the shell method, find the volume formed by rotating the region where x goes between 0 and 4 and y goes between 0 and root x around the y-axis. All right, so let's think about what's happening here. So let's start by sketching our region. So we'll draw some axes here, and what do we have? Well, x is going from 0 to 4, so here's 4, and y goes from 0 up to square root of x. Okay, so let's say this is y equals square root of x. Then our region that we're looking at is this region here. And we'll shade it in, give ourselves a little idea of what's going on here. All right. Now, of course, we also need to mark where we're spinning. So we're going around the y-axis. So when we go around the y-axis, that says we're going this way. Okay, so ultimately when we spin, there'll be another side over here, and that's what we're going to form. All right, so now we have to start thinking. We have to do it both ways, washer method and shell method. Now, there's a couple ways we can think about it, but here's how I like to think about it. And let's just say, let's look at our slices and think about what we're doing. So suppose we were going to slice in a nice vertical fashion. So here's our slice. So vertical fashion says we're going to do integral with respect to x. All right. Now, when we spin, we see, aha, we're getting our little cylinders. So that means we're going to be doing shell method. Okay, so now we'll start with our shell method. So we have our basic setup. Our volume is the adding up from start to finish. So adding up is just another fancy way of saying integrate. And then we have 2 pi, our radius, and that's from our slice to where we spin. And then we have our height, and then that's this part. And then we have our thickness. All right, so those are the pieces that go into the volume. So what do? Well, we're integrating with respect to x. So our thickness is dx. All right, well, that's good. That makes that part pretty straightforward. How about the height? Can we spot that? Yeah, that's also pretty straightforward, right? Because what is it? Well, it's how far we are from the line y equals 0 up to line y equals root x. Well, that is root x. How about the radius? Well, what is that? Well, that's from where we're spinning, which is the y-axis, all the way out to where we currently are at. So in other words, where's our slice? Now our slice moves around. So it's not like our slice is at a fixed value. It varies depending upon which choice of x we are. In fact, our slice is located at x. So I want to say, how far is it from x to 0? And the answer is it's x. All right, so there we go. That's our integral we have to do. Oh, whoops, start and stop. We should mark that. So start at 0. Okay, that's not so bad. End at 4. All right, now we're ready. Now we're ready. So we have, this is 2 pi integral 0 to 4. X times square root of x would be x times x to the half, or x to the 3/2. So we want to write that as a nice power upstairs. Square root of x is not a very good calculus way to write things. Whenever we have a square root of x, we like to translate that and say, hey, this really means x to the 1/2, because that's much more calculus friendly. And then we have our dx here on the end. Well, that's not so bad. What do we do? Well, we would say add 1 to the power, so that would become x to the 5/2, then multiply in front by the reciprocal, 2/5. Good. Almost there. Now we have to evaluate from 0 to 4. 0. Aha! One of our favorite numbers. It's easy to plug in 0. Plug in 0, you get 0. What about 4? Well, 4 to the 5/2. Now you can do it a couple of ways. You could say, hey, 4 to the 5th is what? It's 1,024, right? Right? Is it? It is. Yeah. And the square root of 1,024 is, of course, we'll say it all together, 32. Wait, we didn't say it all together. Okay, what? Okay, now that's really not the way we should do it. When I'm trying to figure out what 4 to the 5/2 is, I should really think of it as there's two operations. I have to the 5th power and to the 1/2 power. And I can choose which way I do it. In other words, I can first take it to the 5th power, then take it to the 1/2 power, or vice versa. Now, in our case, it's probably easier to say, let's take something to the 1/2 power first. In other words, instead of getting big and then small, let's go small and then big. Oftentimes, it's easier to be smaller first, then go to bigger. So, 4 to the 1/2, also known as square root of 4, is 2. Now, 2 to the 5th. Work through your powers. 2, 4, 8, 16, 32. All right. So anyways, where are we at? So this will become 4 to the 5/2, 32. All right. So we have, I'll write that down again, 2 pi times 2/5 times 32. Well, 2 times 32 is 64 times another 2, 128. So 128 fifths pi. There we go. There we go. Good. And that's the volume. But we're not done yet. See, that's the volume if we do it by the shell method. And we said we're going to do it in two ways. So now we're going to do it again, but we're going to use it by washer method. Now, oftentimes, if I want to swap between shell and washer, I also swap between slicing, vertical versus horizontal. So in the first round, we did vertical slice. Second round, that means we're going to do a horizontal slice. So here we go, horizontal slice. So when we see that, well, that says we're really going to be doing our integral with respect to y, because we're just saying it's a small perturbation in y to get that small slice. Okay, well, before we get too far along, we have to say, well, what are our curves as functions of y? In other words, x as a function of y. So y equals square root of x, that becomes x equals y squared. And here, x equals 4 becomes, well, actually it's just x equals 4, so that wasn't so bad. Okay, so here we go, the washer method. All right, well, so how does the washer method work? We add up, start to finish, and the washer says we're taking a slice, and the slice looks like a big circle with a little circle punched out in the middle. So the way you write that is you say, well, it's really the big circle, so pi big radius squared, or outer radius if you like, and minus pi inner radius squared, or small radius if you like. Okay, so this is the area of the cross section, and then you have your thickness. All right, well, time for us to identify what our little pieces are. Well, we know our thickness. That's because we're integrating with respect to y, so our thickness is dy. All right, where do we start and stop? It's not at 0 and 4. 0 and 4 our x. And so, in fact, if you think about the way the integral works, when we have bounds here, this dx says really it's x equals to x equals. And because we have a dy, we want to say, hey, we now want to go from y equals to y equals. So we have to figure out what's the y values. Well, we can see the smallest y value is the very bottom. Y equals 0. We're so lucky. We get a lot of zeros in this problem. What about the highest y value? Well, so we work our way up, and the highest y value occurs over in that corner. Well, what's the y value there? That's at y equals the square root of 4. In other words, this y value, if you were to come across, is at 2. So we're going 0 up to 2. Now, how about our radii? Well, the outer radius. So the outer radius is from where we're spinning to our furthest point away. Well, that distance, it's always going to be the same. It's always going to be 4. So our outer radius is 4. See, it's 4 subtract 0. How about our inner radius? Well, our inner radius is to the inside. So from 0 to y squared, because we want everything to be in terms of y. So how far is it from 0 to y squared? The answer may not surprise you. It's y squared. So that's going to be y squared, right? And don't forget that these are all being squared, so we got to make sure we don't lose that. Okay, so let's see what we have. We have the following. So we have, this is a pi. We can pull that out. Integral 0 up to 2. Okay, those are our bounds. 4 squared, and 16 years ago, no, that's not right. 4 squared is 16. Y squared squared is y to the 4th. And then our thickness, dy. Good. There we go. That's the integral. Now, what's next? Pi, we integrate. Integral of 16, integrate with respect to y, 16y. Integral of y to the 4th. Well, that would be y to the 5th, and then divide by 5, because you have to divide by the new power. All right, evaluate 0 to 2. Good news, 0 is easy. When you plug in 0, you get 0. So we need to plug in 2. So what do we get? Well, we get pi. 16 times 2 is 32. Minus. Now, 2 to the 5th. Well, 2 to the 5th, that's 2, 4, 8, 16, 32. Still 32, same as it was a few minutes ago. It's nice, isn't it nice that it hasn't changed in the last few minutes? Well, we probably wouldn't think that would change. All right. Now, if you look at this, you say, hey, let's go ahead and pull out a 32 really quickly. So, because you have a 32 and a 32. So I can really think of this as 32 pi, 1 minus a 5th. Well, 1 minus a 5th, that's not so bad. That's 4/5. So this is 32 pi times 4/5. And 32 times 4 is 128. So this gives us 128 fifths pi. And that's the answer. Now, we should compare, because we did it 2 different ways, but we were measuring the same thing. And therefore, we shouldn't get a different answer. And luckily, no luck was involved. It was work, and we did it. Workily, that doesn't sound like a real word, but okay. We did the work, and we saw, hey, these answers agree. And therefore, probably a sign we did it right. Well, of course, we did the work. Of course we got it right. All right, so there you go. And you see, again, there's different options. And sometimes you might say, hey, I thought the shell method was a lot better. And it's sometimes the case that, yeah, the shell method works a lot better. And of course, sometimes it's the opposite. It's good to have the ability to go between both. All right, well, one problem down. Time for some more problems. All right, so I happen to have another problem. So here we go. Rotate the region in the first quadrant bounded by y equals root x and y equals 2 root x minus 3 around the line y equals 2. Find the volume of the resulting shape. Okay, so here we go. Let's think about what's happening here. So we have y equals square root of x, or root x. All right, it's doing something like that. And y equals 2 square root x minus 3. Now, you'll see that x minus 3 says, hey, you really come over here to 3, because that's what that x minus 3 on the inside of the square root does, is it's a shift over. So we shift it over. All right, after you shift over, then what? Well, it looks like square root, but it goes up steeper. So we've shifted, but it also goes up steeper, and so maybe it does something like that. And so what we're getting is a shape kind of a little bit like a fin. So here's our fin. And now that's our region. And the other thing it says is let's revolve this around the line y equals 2. Now, before we draw where y equals 2 is, we might ask ourselves the question, can we figure out where they intersect? Now, there's a couple of ways to do that, and here's one way. One way to do it is to say, well, they intersect where they agree. Okay, so what would be true? We would need to have square root of x would have to equal 2 square root of x minus 3. If we square both sides, that gets rid of the square root. That would say that x is equal to 4 times x minus 3, which is equal to 4x minus 12. Move the 12 and the x across, we get 3x equals 12, or x equals 4. All right, plug in 4 just to check. Square root of 4 is 2. Then we have 2 times the square root of 1 is also 2. So here we go. This would be at x equals 4 and y equals 2. And now we say, we're actually spinning around the line y equals 2. So this is where we're going to spin. All right, so there we go. We have our setup, we have our shape, we have the line we're spinning around, and now we ask ourselves the question, what's the volume? So there hasn't been any command about which way to find the answer. In other words, we don't have a restriction. We could use a washer method, or we could use a shell method. So let's think about it in terms of slicing. So suppose for a second we were to do vertical slicing. In other words, we say, hey, we started with functions of x. Maybe we should stick with functions of x, and that'll give us our best answer. Well, when we say our best answer, what we really mean is the one that's easiest to work out. Now, if we think about what happens as we do vertical slicing, we notice something happens that's not going to be very nice for us. And it happens at 3. Can you see something here? Notice that before 3, we go from the top curve down to 0. So the top curve, this is square root of x. And then here is 0. I'll add some little y equals square root of x, y equals 0. After 3, there's a transition. And what happens is now we still go from square root of x on the top, but downstairs we go to y equals 2 square root of x minus 3. So what does that mean? It means if we're going to do vertical slicing, what we'll have to do is we'll have to split the problem into 2 parts because there's a change of behavior. There's the before 3 and the after 3. Since they behave differently, we have to do them separately, which means we'd have to do 2 integrals, one for each part. That sounds like twice as much work as I'm willing to do. Now, it might be unavoidable, but let's see if we can look at the other option. Now, the other option is instead of slicing a vertical way, we slice a horizontal way. So let's see where that would take us. So if we were to slice horizontally, we just sort of do a quick check, might see, it looks like, yeah, see, all the way up, we always are consistent. We always go on the left, square root of x, on the right, 2 root x minus 3. One consistent behavior the whole way, which means one integral to do. That sounds promising. So let's do horizontal slicing. Okay, so far, all we've done is come to the conclusion horizontal probably is going to be a better way to go. Now we have to start thinking about, well, now that we know it's horizontal slicing, what method does that correspond to? Well, we take our horizontal slice and we spin it and we ask ourselves the question, what shape do we see? And we see a shell, a cylinder. So we're going to be using the shell method. Not really a big surprise. We kind of anticipate it might be a shell method, since after all, we've been talking about shell method, and that's what we're practicing. Okay, so let's write our basic formula. So if we're after our volume by shell method, we're adding up, which that means the integral, from our start to our stop, beginning to end. We have 2 pi radius, that's the circumference of the shell. Our height, that's the height of the shell, kind of a descriptive name. And the thickness, which is the thickness of the shell. Yeah, see, these are all very descriptive because that helps us see what's going on. Now, because it's a horizontal slice, our thickness is going to be our change in y, because the thin change, that small change, is with respect to y. So that's easy for us to identify. So there's our dy. Now that we know what we're integrating with respect to y, we have to say, well, where does y go from? Low value of y to high value of y. So in other words, as we slice, where do we start and stop? Well, the low value is at 0. The high value, at 2. So we're going to go from y equals 0 all the way to y equals 2. All right. Good. Good. Progress. Good progress. Now, 2 things left. The radius and the height. Let's talk about the radius. So for the radius, that would be from our slice, and our slice we're thinking of as being a y to where we're spinning. So in other words, the radius is really that distance right here. So that's the radius between 2 and y. All right, so what is it? Is it 2 minus y? Is it y minus 2? Pay attention, because otherwise we might lose a sign. We don't want to lose any sign. We want to get all of them, because after all, our goal is to get all the points. Got to get them all. So in our case, we say, okay, radius is a measurement, should be positive, so we're going to make sure we take high minus low. So 2 is above y. So our radius, high minus low, 2 minus y. Okay, finally, our height. Well, the height of the shell is the length from the one side to the other side. In our case, it's going to be right and left. Now, currently, we have y's as functions of x. We need to swap the roles. Some of them are not so bad. Y equals square root of x becomes x equals y squared. This one, we'll have to think a little bit. So y equals 2 square root of x minus 3 becomes what? Well, if we divide by 2, a half y equals square root of x minus 3. All right, square. So 1/4 y squared equals x minus 3. All right, one more step. We're going to add 3. So x equals 1/4 y squared plus 3. Okay, so that's our right and our left, where we have x as functions of y. So we're going to take our right, subtract our left. That gives us our distance. That's our measurement. So this will be the right hand, 1/4 y squared plus 3, subtract the left hand, y squared. All right, and there you go. There you go. Okay, so let's clean this up. So we can pull out the 2 pi. That's a constant, 2 pi, integral 0 up to 2. And then we have 2 minus y. And here, let's see, 1/4 y squared minus y squared. Well, that's like minus 3/4 y squared. And then a plus 3, so we'll write that as 3 minus 3/4 y squared. Good. dy. All right. The setup is done. But we still want an answer. It wasn't just setting it up. Let's find an answer. So that's our next step. So to do that, we have to start thinking about how do we integrate. Well, the good news is that these are polynomials, so that makes it a lot simpler. And let's go ahead and pull things out. So for instance, in this second term, both terms have a 3. There's a 1/4 here. Let's go ahead and pull a 4th out. So I'm going to pull 3/4 out of this piece so that I have 3/4. From the first term, I'd be left with a 4 and then a minus y squared. You can see that it would be 4. Just imagine multiplying back in. 3/4 times 4 would in fact give you 3 and minus 3/4 y squared. That's a constant. I'm going to pull it all the way out. So 2 pi times 3/4 will give us what? Well, the 2 and the 4, we can get a little bit of cancellation there. So we're at 3 pi over 2, integral 0 to 2 of 2 minus y times 4 minus y squared, dy. Now, multiply, or if you like, FOIL. So we're going to do our foiling. Good practice, right? In fact, you know, calculus is a great time to really hone your algebra because there's lots of opportunities. 2 times 4 is 8, then minus 2y squared, then minus 4y, and plus y cubed. And right now, well, none of these terms combine. They're all different powers of y. Okay, so in that case, we just integrate. So we end up with 3 pi over 2. Then we have 8y minus, this will be 2/3 y cubed. Then here, we'll get minus 2y squared. And then finally, plus y cubed, integral of that is y to the 4th over 4. Evaluate from 0 to 2. All right, well, good. Progress. Well, that's what we want, right? So, what happens? Well, if you plug in 0, you get 0. That's good. What happens if you plug in 2? Well, time for some patience. So, what do we have? We have the following. We have 3 pi over 2. 8 times 2, 16. 2 times 2 cubed, well, that's 2 times 8, which is, again, 16, so minus 16/3. 2 times 2 squared, well, that's 2 times 4, that's 8, so minus 8. 2 to the 4th, so that's 2, 4, 8, 16. And then we're going to divide by 4, so plus 4. Okay, now 16 plus 4 is 20, subtract 8 is 12. Multiply by 3/2. Okay, we're running out of space. Let's do a little bit of work here. So 16 minus 8 plus 4 was 12. If you divide by 2, that's 6, times 3 gives us 18. So 18. So that's the 16, the 8, and the 4 times 3/2. If we take 3/2 and we multiply that by 16/3, well, the 3's cancel, 16 divided by 2 is 8. And don't forget the minus. So 3 halves times minus 16 thirds would give us minus 8. 18 minus 8 is 10, giving us a final answer of 10 pi. Whew. There was a little bit of work to get to that, but we got there, and we just had to be patient. It's good to be patient. And if we're just methodical, work it through a little bit at a time, we can get to the answer. Now, the good thing is we ended up with a positive number. If we had ended up with a negative number, we would have to say, whoa, slow down. Something has happened here that should not have happened. Let's go back and check our work. Because when we talk about volume, volume is a measurement. It should be positive. All right, good. These are good problems. Really lots of fun testing this out. All right, our next problem. Find 2 pi integral 0 to 1 of x arctangent of x dx. Now, depending upon how much math you know, you might say, I know how to do this problem. I'm going to use boom, 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 boom. But we haven't learned about boom, 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 boom. Maybe. Okay, we don't know. It depends. It depends on the order in which you're covering topics. So there are ways to integrate x arctangent of x that have nothing to do with the shell method. But we're talking about shell method, right? And so we should start thinking about, hey, maybe there's a shell method connection. Now, you might say, but there wasn't anything about a volume here. They just said, here's this integral. Now, there's an important idea here, and I think it's one that's worth being very explicit about. And that is, we reserve the right to interpret any integral to our advantage. By that I mean, regardless of where the integral came from, we can look at it and say, yes, it may have started as this type of thing, but here's how I choose to think about what it represents now. So when I look at this, I spot right away a couple of things. There's a 2 pi. Okay, well that oftentimes shows up when we talk about things like the shell method, because the shell method has a 2 pi. And then there's something that's an x, and then there's an arctangent of x. Now x, oftentimes, maybe this could be a radius, because the radius is going to look like x minus something or something minus x. So when I'm looking for a shell method, I say, hey, I want there to be an x involved. And then arctangent of x, maybe that could be thought of as a height. So we start thinking about it and say, let's think about it and see if this makes sense. So what could we do? Well, we start by the arctangent function. So here's arctangent, does something like this. So here's y equals arctangent of x. And we said, what's going on here? If this were representing a volume, then it would represent the following. You would be going from 0 up to 1 of this function, y equals arctangent of x. And now, what do you have? Well, let's see. I'm going to make some notes here. Shell. What would it be? Well, it would be our slices would look like little thin vertical slices, because we're integrating with respect to x. That tells us that we're integrating vertical slices. And now we say, okay, our radius would be our x, because that's our thing that looks like a radius. So we say, aha, here's our interpretation of what the integral represents. So, all right, I probably have misspelled interpretation before. I did not do very well in the spelling bee when I was a kid. So let's imagine I could spell interpretation correctly. All right, so what is our interpretation? It says we're going to take the region where we have 0 less than or equal to x less than or equal to 1, and 0 less than or equal to y less than or equal to arctangent of x, and we spin around the y-axis, and we want to find the volume. All right, so this integral can be interpreted in that way. Perfectly valid interpretation. Absolutely perfectly valid interpretation. So we say, hey, what are we trying to do? We're trying to find a volume because that's our goal. Let's find the volume in a different way. So now we say, how else could I find a volume? Well, instead of doing vertical slices, let's do horizontal slices. All right, so here we go. We're going to start thinking slice in a horizontal manner. So if we slice in a horizontal manner, what's going to happen? See, currently, if we look at our little spin around, what we have in our original interpretation is we're getting little shells. But in our new interpretation, where we're doing our horizontal slicing, we see that what we'll get are little tiny washers. So we're going to do washer method. Okay, so our washer method says what? Well, our formula volume is add up, start to finish, pi, the outer radius squared, minus the inner radius, or the small radius, squared, and then our thickness. All right, that's our setup. That's how we find things using the washer method. Okay, so let's start thinking. We have to start identifying certain things. Now, our thickness, what will that become? Well, that's going to be our dy, because we're doing horizontal slices. That's dy. Where do our bounds go from? Well, we need to know where does y go from. And we can see part of it, we start low. That's y equals 0. Okay, start at 0. And then go to where? Well, we got to go high, up here. What is that? Well, that would be, where's this y value? Well, what is arctangent of 1? Arctangent of 1 is pi fourths. All right, so that's our high value, 0 to pi over 4. Now, what about our outer radius? Well, that's from 0 to 1, because it's always 1. So that's 1. That's easy. What about our inner radius? And here's where things get fun. Y equals arctangent of x means x equals tangent of y. So our inner radius, this little space here, is tangent of y. So we have tangent of y, and that's being squared. Okay, good. Well, what does that tell us? It tells us that we have the integral 0 to pi over 4 of pi 1 minus tangent squared y dy. All right, now that finds the same volume. And therefore, this integral is equal to that integral. So we've now transformed our problem from one integral and saying, hey, if I want to find my original integral, it's equivalent to finding my new integral. Now, of course, the question is, how do you find this new one? Well, the one, we love it. Tangent squared, not so much. Tangent squared is not on our list. But we start thinking, hey, that looks trig. And one thing we know about trig is there's always identities. So we start saying, is there a nice identity that connects tangent squared to something we can integrate? Well, our basic things are sine, yeah. Cosine, yeah. Secant tangent, yeah. Secant squared, ah, that's right. Secant squared has a nice connection to tangent squared. So you might remember that tangent squared plus 1 is equal to secant squared. So now we say, hey, what does this allow us to do? It says I can take this tangent squared, which I may not be very comfortable with, and rewrite it using secant squared. So in particular, we can replace tangent squared by secant squared minus 1. Now, be careful here. Keep track, because there's a minus in front. So it's not that these ones will actually cancel, because when you go and distribute this minus sign through, they actually combine. So, what are we up to? Well, we have the following. We have the pi in the front, 0 to pi over 4. 1 minus minus 1 is 2, minus secant squared y, and dy. Well, these are things we can integrate. Integral of 2, 2y. Integral of secant squared, tangent. See, that's why we wanted to change it. We wanted to change tangent squared to secant squared, because then we'd have something we can integrate. So 2y minus tangent of y, evaluate that from 0 to pi over 4. So we plug in. So this is pi, 2 times pi over 4, pi over 2. Tangent of pi over 4 is 1. It's a nice value. Now plug in 0. 2 times 0, 0. Tangent of 0, 0. So we end up with 1/2 pi squared and minus pi. And there we go. That's our answer. So we were able to find this integral, even though we haven't really talked about the, we were able to go through and figure it out by using our power of interpretation. We were able to interpret the integral in a nice way, and that gave us the ability to see, aha, here's a better way to think about what we're looking for. Good problem. Great problem. So let's do another great problem. Of course, that's not hard. We always do great problems. We're just so lucky to be doing calculus, full of wonderful problems. Find the volume of the solid formed by rotating the region where y is between 0 and x over x squared plus 1, and x goes from 0 to 1. Around the line, x equals -1. Okay, let's think about that. Now, x going from 0 to 1, that's not so bad, but I'm not really sure what x over x squared plus 1 does. I can see it's going to be 0, then I can see it's going to be positive because there's certainly nothing negative. Now, in the long run, well, the x is a lot smaller than x squared in the long run, so it's going to go up, and eventually it's going to come down. I don't know if it comes down before or after 1. Maybe it comes down like that. Maybe not, I don't know. But that's our shape. And where are we spinning? Well, we're going to spin around this line. X equals -1. All right, so we have our shape. Here's our nice basic shape. So now we start to think, okay, how do we go about solving this problem? Well, good question. Good question. So, what can we do? Well, should we slice horizontally or vertically? Now, if we were to slice vertically, I don't think it'd be so easy, because we'd have to find the inverse of this function. Y equals x over x squared plus 1. It's not so clear that there's a nice simple way to write x as a function of y. And even if we do, it could get messy if in fact it does come down. Things could get complicated, and we don't want things to be complicated. In fact, our goal, whenever we're doing problems, is let's try not to be complicated. And in this problem, we said, well, look, the primary way things are given to us is y is given to us as a function of x. So y equals x over x squared plus 1. It really suggests we should start by thinking of slicing in a way that incorporates x. In other words, we really should think about doing our vertical slicing. So that's how we incorporate x. And as we spin, we see, aha, when we spin this, the shape that's going to get formed is going to be a shell. So we're going to approach this by using the shell method. All right, good. So let's go through and run our setup here. So our basic formula for the shell, volume is integral, which means we're really adding up our start to our end, 2 pi, our radius, our height, and our thickness. All right, so there's our shell method. Okay, so now we need to start thinking about these little pieces and how we can fit them all together. All right, so we know a couple of things right away without much work. Because we're slicing vertically, it means our thickness here is our dx. Because you can see there's just a very, very tiny change in x when we're talking about our thin vertical slice, which means our bounds need to be x bounds, and the x bounds are already given to us, going from 0 to 1. Oh, freebies. Nice. I like it when we get things for free. It makes things a lot easier. So 0 to 1. Okay, what else do we need? Well, how about a height? That one I think we can get pretty quick. Our height is this distance from this curve, x over x squared plus 1, down to this curve, 0. So it's the function, x over x squared plus 1. Our radius. Okay, now, I think this one might be the one we need to be careful of. What's our radius? It's going to be from where we're spinning to our slice. Now our slice is at an arbitrary value for x, where we're spinning is at -1. So what's the distance from x to -1? Well, we take the difference. Is it x subtract -1 or is it -1 subtract x? Well, it's going to be the right minus the left. So it'll be x minus -1, or if you like, it's x plus 1. Now, x plus 1 makes sense if you think of the picture, because what do you have? X is the distance to the axis, and then you have a plus 1, because you still have to go all the way over to -1. Okay, so it works out. Good, good. Okay, well, let's clean it up. So what does this become? This becomes our integral, 0 to 1. We have our 2 pi. Then I have x plus 1 times x. So I'm going to go ahead and multiply that out. That's x squared plus x over x squared plus 1. And dx. And at this point, we are probably thinking like, how can we do this? Well, there are certain tools that help us work with these types of functions. These are called rational functions, which means a polynomial over a polynomial. But let's not try anything fancy. Let's just think about what we can reason. Now notice the denominator is x squared plus 1. I kind of almost have that upstairs. I have the x squared, it's just plus x, not plus 1. So let's do something. This is a wonderful tool. I don't want to call it a trick, because a trick implies it only works once. A tool works more than once, and I think this works many times. So our tool here is to say, hey, let's do something called add and subtract. So our goal is I want to look like the x squared plus 1 downstairs, because that helps me do something. So I'm going to say I want an x squared. That's already there, and a plus 1. So I put a plus 1, but then I say, whoa. I don't have a plus 1 upstairs. So that's where the minus 1 comes into play. So minus 1 and then plus x. Okay, why the plus x? Because there was already a plus x there. Okay, so let's see what we really have here. So what we have is, I'll go ahead and pull the 2 pi out. 2 pi integral 0 to 1. The x squared plus 1 over x squared plus 1 is nice. That's 1. Then we have minus 1 over x squared plus 1. Also nice, because 1 over x squared plus 1 is a nice integral to work with. It's one of our 10 basic integrals that we know by heart, and one of my personal favorites, arctangent. tangent. Oh, what a great integral. Okay, and then there's the x over x squared plus 1. And this one turns out to also be pretty nice. Okay, indeed, we can actually go through and do these integrals. Now, let's talk about the last one. The first two are pretty much freebies. The last one is almost. So I have x squared plus 1. I have x. One of the things you start to learn to spot are things like, well, if I have a function downstairs and a derivative upstairs, the derivative of x squared plus 1 is 2x, really close to x. So I'm going to do something similar to add and subtract. Now I'm going to multiply and divide. So think of it as I'm going to put a 2 here and then a half. If I do that, it's the same as multiplying by 1. And now, what do you have? We have a function downstairs, derivative upstairs. That's a log. And so let's write out what we have. So we have 2 pi. Integral of 1 is x. Integral of 1 over x squared plus 1. Arctangent of x. And then 1/2. And now the integral of 2x over x squared plus 1. Well, this is one that hopefully we can do in our head. Think of it as u equals x squared plus 1. Du would be 2x dx. So it's 1 over u du, natural log. So it's a natural log, in our case, of x squared plus 1. Now, if you don't believe me, take the derivative of 1/2 natural log of x squared plus 1. You'll get the half, 1 over x squared plus 1, times by the chain rule, 2x. So it works out. Don't forget this is a definite integral. All problems and applications are definite integrals because we're looking for a value. We're trying to measure something. So what's our last thing to do? Plug in 0 and 1. Now let's plug in 0 first. 0 is 0. Nice. Arctangent of 0 is 0, which is great. 0 squared plus 1 is 1, but log of 1 is 0. So plug in 0, it all goes away. How about plugging in 1? Well, if you plug in 1, we get the 2 pi in front, a 1, then minus arctangent of 1. We know what arctangent of 1 is. It's pi over 4. Then plus 1/2 natural log of 1 squared plus 1. Well, that's going to be natural log 2. And finally, we can multiply the 2 pi through to all the little pieces. So we get 2 pi minus the 2 and the 4. So that would be 1/2 pi squared. Here are the 2 and the 2. So plus pi natural log 2. And there you go. That's our answer. Wow, that was great. Good. Well, again, just be patient. Work the problem. Be methodical. And we get there. That's the important thing, is that we get there. All right. Well, we should probably do another problem. Of course. Let's do another problem. So, let f of x be something which is greater than or equal to 0 for x between 1 and 4. Okay, well that's interesting. So we really don't know much about what f is. All we know is it's doing something. So what do we have? Well, let's just say it does this. Maybe, probably not. We don't know, but it's doing something. There's 1, there's 4, and here's our region. And the reason I want to do that is I just sort of want to get an intuition about what's happening here. So we have some region. All right, now we're also told some information here. So let's go through and parse this. Given that when we rotate the region, here's our region, between f of x and the x-axis, between x equals 1 and x equals 4, around the x-axis, the resulting volume is 32 pi, while if we rotate the same region around the y-axis, the volume is 48 pi. Okay, so we're told something. We're told that when we spin around the x-axis, we have the shape will be what? Volume equals 32 pi. And then over here, when we spin around the y-axis, so around the y-axis, we get that the volume is going to be 48 pi. And now, our problem. Find the integral from 1 to 4 of f of x minus x quantity squared. Now, our initial reaction is, we don't have enough information because we don't know what f of x is. How can we possibly figure out what the integral of f of x is if I don't even know what f of x is? So that seems disheartening. But on the other hand, it is a problem, so we should be able to solve this. So we've got to start thinking about what can we do. So let's start by saying, well, let's take the information we have and write it in some convenient form. Now you might be saying, we don't have very much information, but we do have some, right? See this information here? It says, when I take our region and I go around the x-axis, so we're spinning around the x-axis, I know my volume is 32 pi. But we also know how to compute that volume. So if we think about it, well, what do we have to do? We can't slice horizontal because we have no idea what the function is doing. The only chance is to slice vertical. So if we slice vertical, and we spin around the x-axis, well, this should really be a shell method. And what do we get? Well, we get that disk. I got ahead of myself. See, if I spin here, I'm going to get a disk out. So we have that 32 pi, which is our volume. Well, according to the disk method, you integrate a to b pi, and it's the radius. There's only one. There's no hole. It's not a holy object. It's a solid object. And we have our thickness. All right. So for us, we get that this is pi integral 1 to 4. And then our radius is the height of the function. So that would be f of x quantity squared dx. Now, what that really tells us, because I can cancel the pi's here, is that the integral from 1 to 4 of the value f of x squared is equal to 32. All right, good to keep that in mind. Okay, now, how about this piece of information? Well, here, if we spin, our shape is going to be a shell. So this is going to sweep out. And now we're in the shell method. Okay, so this is our shell. So what do we have? Well, we have our volume, 48 pi, is, shell method, would be integral a to b of 2 pi, our radius, our height, and our thickness. All right, so in our case, we go 1 to 4, because we're doing a vertical slice. That's the only thing we can do. So vertical slice, we're saying, where do we start and end? Start at 1 and 4. Our 2 pi, our distance to the y-axis is x. So that's x is the radius, and the height is f of x. And our thickness is dx. So similar idea as before, we can say, aha, let's cancel a pi, and we can say that the integral 1 to 4 of 2x f of x dx is 48. Okay, now, those are our two pieces of information rewritten using our formula. What can we do? Well, now we start to say, hey, let's actually work on this integral and see what it becomes. So I need to square it. So what is that? Well, integral 1 to 4 of f of x squared, then minus 2x f of x, and then plus x squared dx. So, well, I can think of this as three pieces. 1 to 4 of f of x squared dx, then minus integral 1 to 4 2x f of x dx, and plus integral 1 to 4 of x squared dx. But we've got great news. Our great news is we know some of these pieces. So, for example, the integral of f of x quantity squared from 1 to 4 is 32. And the integral of 2x f of x dx is 48. We don't know this last one, though. But wait, the last one doesn't involve f of x at all, which means we can just integrate it. So let's integrate it, and let's see what we get. So let's see, this would be 1/3 x cubed, evaluated from 1 to 4. So that would be 1/3. 4 cubed, well, 4 times 4 is 16, times another 4 will give us 64. So 64, so that's 4 cubed. 1 cubed is 1, 64 minus 1. 64 minus 1, 63, and 3 goes into 63, giving us 21. So what do we have? We have, at the end, we have all our three pieces. So we have this is equal to 32 minus 48 plus 21. Well, 32 plus 21 makes 53. Subtract 48 gives us 5. And that's the answer. So even though we don't know what f of x is, that's okay, because we can take the information given to us and translate it into something which helps us solve the problem. So it's just a matter of saying, work with what you have. Say, let's start with the givens. In this case, our givens are, we have information on volumes. Take that and transform it into something useful. And once you have something useful, say, okay, how do I use that information with the problem I'm given? So this is fun. I like this problem. I know I have so many favorite problems, but this one is just one of those things that doesn't feel like we can do, and then we do it. And that just feels so, so good. Okay, good. Good. Okay, and that's going to bring us to our very last problem. Don't worry, there's always going to be more problems later on. But for now, our last problem for this session. Find the volume created when the region in the first quadrant, bounded by the x-axis, the y-axis, and y equals the square root of 1 minus x to the fourth, is rotated around the y-axis. Okay, so let's think about what we have here. So what we have is, we'll sketch it here, the x-axis and the y-axis, and then this sort of strange curve. It's not a circle. See, a circle would be y equals the square root of 1 minus x squared. So it's not a circle, so it's not perfectly symmetrical, but we can kind of see it's almost it's circle-like. And for example, when x equals 0, we get that y equals 1. When x equals 1, we see y equals 0. So let's say it looks something a little bit like that. So I just want to emphasize, not a circle, but it has this sort of flavor to it. So here's our basic shape. And now what we're going to do is we're going to take this region here, and we're going to rotate this region around the y-axis. Okay, So let's spin this around the y-axis. Now this is probably something that we could do either by using the washer method or disk method or using shell method, but let's just see where we go. Since it starts by saying, let's think of things in terms as functions of x, that really suggests we should be doing our vertical slicing. So I'm going to think about where that takes us. So here's a vertical slice, and I say, all right, if we do a vertical slice and we spin, the result is going to be a shell. So let's use our shell method. Probably at this point you're saying, well, of course it's going to be a shell method. That's what we're practicing today. But still, it's like, how do we get there? See, a big part of learning math is not just saying, oh, here's a tool. Another part of math is saying, hey, which tool do I need to grab? And recognizing, aha, this is a shell tool. Let me go pick up the shell method. So that's why we want to start reasoning. Why am I doing this? Why am I not doing that? Because that helps us know what to do and when. Okay, so our basic formula. Volume is equal to our integral from start to finish. In other words, we're really adding up. That's what integration is about. Our 2 pi, our radius, our height, and our thickness. Okay, so that's what integrals look like when we're doing the shell method. Now, a lot of this is pretty straightforward. No big surprises. We can see our thickness because we're looking at these nice vertical slices that our thickness is really a dx. Where does x go from? Well, we start at 0 and we end at 1. So these are our x values. I want to be clear. I'm not going 0 to 1y, I'm going 0 to 1x because that's our slicing, right? Da, 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 da. We're going this way. Da, 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 0 to 1. All right. Our radius, well, that is how far are we from where we're spinning? Well, so I'm going from x to 0. So that's x. And our height. What is our height? Well, that's how high up and down we are. So that would be the height is the square root of 1 minus x to the 4th. All right. So what do we have? We put it all together and we get the following. So this is equal to the integral 0 to 1 of 2 pi x square root 1 minus x to the 4th dx. Okay, so here we go. How do we integrate something like this? And hopefully do it without going too crazy. Now, square roots, they are a challenge. And part of calculus is saying, hey, how do we learn to deal with square roots? It's a non-trivial thing. We want to be careful because there's a lot of times students are like, well, I'll just make it really easy. Oh, the square root of 1 minus x to the 4th would be 1 minus x squared, right? I just take the square root of the first term, subtract the square root of the second term. And the answer is no, that's not how it works. And it's not just because we want to make math complicated enough that we keep our jobs. It's truly just, it's not how it works. You can't do exponentiation on individual terms when you have things being added and subtracted. So we start thinking about, okay, this is not one of our basic integrals that we can do automatically. So let's think about things we can start doing. So arithmetic or really algebra, trig, or substitution. Well, there's no trig involved. Not yet, probably won't be. There's nothing really that jumps out for algebra. So what about substitution? If we think back to substitution, we can start saying, well, one of the things you can look for when you have substitution is there's a hint in substitution. We maybe should remind ourselves how we find that substitution. So remember, when you're looking for a substitution, there's 2 places to look for a substitution. And the 2 places are, you look for a function in a function, because substitution is an inside job. So you say, okay, what's something on the inside? Now, the problem is, sometimes the inside function has been obfuscated because we've rewritten it in a slightly different way. But the other place to look for is saying, oh, there's this g prime of x. So if I see, hey, there's a piece of this function I recognize as having a nice derivative of something, that can be a clue as to the substitution I make. So looking at this, I look and say, does any of this look like a good derivative? And I see something. Do you see it? That 2x. Oh, that's a very tempting. What function, when we take the derivative, gives us 2x? The answer is x squared would do it. So let's think about that substitution. So if we do the substitution equals x squared, d would be 2x dx. So what do we have? Well, we've gone the 2x dx, that's part of our du. We don't have the pi. Let's pull that out. So pi, okay, 2x dx becomes our du. What about the square root of 1 minus x to the fourth? Well, x to the fourth, how does that connect to x squared? Well, it's x squared squared. So this becomes the square root of 1 minus u squared. All right, true. Okay, good. What about the bounds? Okay, now here we have to be careful. See, the original bounds, these are our x bounds. So we're going from 0 to 1. That really means we're going from x equals 0 to x equals 1. That's what these bounds mean. When we do substitution, we change from x to u. So everything changes. So our bounds also change. And so our old bounds are 0 to 1. Those are the old bounds, the x bounds. They're not the u bounds. So we are no longer going from 0 to 1, and now we're going from 0 to 1. Aha! Now you're probably thinking, what? Did you really change? And the answer is yes, because we're going from u equals 0 to u equals 1, when before we were going from x equals 0 to x equals 1. It just happens to be the case that 0 squared is 0, and that 1 squared is 1. But we're actually changing our bounds. Don't just take it for granted that nothing happened. Something happened. Okay, so now we're like, all right, that's a little bit easier thing to work with, but we still have this integral. How do we do it? Okay, now, it's not just any integral. This one you might recognize. Do you see it? It's a circle. Ah, it is a circle. Indeed, I can think of it and say, hey, this corresponds to an area of a circle. Well, in particular, what circle? Well, it's 1/4 of the unit circle, because I'm going from 0 to 1 up to the square root of 1 minus u squared. So really, I should say area of 1/4 of a circle. So I say, well, that's not so bad. So that's pi. If I were to draw the whole circle in, the radius is 1. So the area of pi r squared would be pi. 1/4 of that would be 1/4 pi, which gets us to a final answer of 1/4 pi squared. Now, let's pause for a second and let's ask ourselves a question. One, is that legal? And two, isn't that weird? Now, I think the answer to number two is it's a little bit weird the more you think about it. The answer to number one is yes. Now, why should we have any concern at all? Here's the thing that might throw people off. When we started, what did our integral correspond to? It corresponded to a volume. When we figured out the integral here, what did we use as an argument? An area. Are we allowed to say, oh, this integral which came from representing a volume, I can now interpret as an area? Is that possible? And the answer is absolutely. You are allowed to interpret the integral in any way you want. And that ability to change interpretations gives you a lot of power and a lot of flexibility. And so you want to think about, okay, how can I reinterpret what I'm working on right now to help me have the best chance of success. And that's one of the powerful tools. When you master that skill of saying, hey, I can reinterpret this to my advantage, you're going to gain a lot of power. And then you're really starting to get into the part where now math becomes fun. It's like, what can I do with this? How can I think of this in a different way? And we really want math to be fun. After all, it's going to be a large chunk of time in our near future. And so, well, let's keep having fun. That's it for today, but keep working.